Hi, my name is Katharina Predel. I'm the program manager for VCSEL and LED testing at Instrument Systems, and I'm going to talk about the characterization of VCSELs in terms of eye safety according to the IEC 6825-1 standard. VCSELs have gained quite some attraction in 3D sensing applications, such as, for example, in consumer electronics. You all may know the Face ID technology employed in the iPhone. They have become quite popular as LiDAR systems in autonomous driving and also in novel human-machine interfaces, such as, for example, in AR/VR. VCSELs are so-called vertical cavity surface emitting lasers, which is basically a laser diode with a certain emission characteristics. And as any kind of laser, they may potentially cause harm to the human eye and also to the skin. And that is why they require eye safety evaluation for safe use in public. Now, why is eye safety so important? The human eye is an optical system that is greatly optimized to sharply image visible light onto the retina. And in terms of laser light, which is coherent and strongly directed, this has great potential to destroy the retina because you cause high intensities on the retina and also in the eyeball. So laser safety is all about the question of how much energy is either absorbed in the eyeball or imaged onto the retina. And this is exactly what the IEC standard is all about. So it gives both the users and the manufacturers all guidelines, regulations, and instructions to allow for safe laser use. And it says, for example, I cite here, it is the responsibility of the manufacturer to ensure that the accessible radiation, that is the part of the laser light that may be absorbed by the eye, that may enter the human eye, does not exceed the AEL, that is the accessible emission limit of the assigned class. We will come back to laser classes on the next slide. It also says that your measurement equipment, if you are a manufacturer that wants to evaluate your laser system, your measurement equipment should be calibrated and traceable to national standards. And that is to ensure the accuracy needed for safe evaluation. I recommend here as further reading the corresponding tech report, measurements for classification of laser products, and also the IEC 610040 standard, which is power and energy measuring detectors, instruments, and equipment for laser radiation. I just mentioned laser classes. So what's a laser class, basically? Laser classes indicate the potential harmfulness of your system. A laser class 1 is always safe. It may be used by non-trained personnel, by kids, in public domains. You won't harm anyone with a laser class 1. On the other hand, a laser class 4 is super dangerous, not only to the human eye, but also to the skin. It may cause burns. And the damages are not only due to direct beam viewing, but they may even be due to indirect reflections or diffuse scattering and so on and so forth. So the bottom line here is, if you want to use a laser in public, it better be laser class 1. There's a little specialty for visible lasers. They also may be laser class 2. That's a special class for visible lasers, and that takes into account the fact that you will see the laser beam as soon as it enters the eye. You will just realize that there's a flash, and you will react on that with the blinking reflex. So you will close your eyes at some point. Since we are talking about 3D sensing applications that mostly operate in the NIR region, our lasers must be laser class 1. Now, before I will explain you of how to evaluate laser class or determine a laser class of a certain system, we need to talk about the special characteristics of VCSELs and their beam geometry. So the first thing that distinguishes a VCSEL laser from a normal Gaussian lasers is that they are operating multimode. So they won't emit a Gaussian TM00 beam, but the beam pattern, you can see it here, will more look like a flower or moon shape, or it's round, but it's not very symmetric, or not very regular, I'd say. The next thing that is important to notice is that VCSELs are highly divergent as compared to regular lasers. So they cannot be considered collimated. They will have a divergence of 10 degrees or more. And also, depending on what kind of optics they have in front, they are not necessarily symmetric. The third point is that many applications require VCSEL arrays. That is the picture you see on the right-hand side. So normally you will deal with modules that do not only have a single emitter, but many hundreds of emitters. And that will cause, or that will result in a so-called extended source. We will come back to this later. And as a last point, they are often equipped with additional optical elements, so-called DOEs, diffractive optical elements, such as, for example, diffusers or the quite popular dot pattern generator that you may know from the Face ID. Now here comes laser class assignment. This is the flow chart you need to follow when you want to characterize your VCSEL in terms of eye safety. Looks complicated, but we will go through it step by step. The first thing you need to determine is whether your laser is pulsed or in continuous wave, so-called CW mode. And when I talk about pulsed lasers, I also mean lasers that are scanning. So they may be CW, but if you have a mirror, a rotating mirror, or some MEMS mirror that steers the laser, it will be considered pulsed. We are talking about pulsed lasers, so I will ignore the CW classification here. Okay, for a pulsed laser, you need to determine a couple of parameters. First thing you need is the laser wavelength. You also need the pulse energy, and you need the average power, you need the pulse width, and you need the pulse repetition frequency. As you can see on the downside here, these are the parameters that you need to measure. Maybe one thing about the spectrum of a VCSEL as compared to normal lasers, they do not look very smooth. You see some side modes. There's always side modes in VCSEL evaluation. So for laser safety assessment, the lambda parameter should be the centroid wavelength and not the peak wavelength. One thing I need to mention when talking about pulse energy or average power is that due to the high divergence of VCSELs, not all the light may enter the human eye. It's most probably only a small part. That says that you need to assume a 7 millimeter aperture that mimics the pupil of the human eye in a 10 centimeter distance. And this is the part of the light you need to consider for your power and energy determination. In terms of VCSELs, you do not only have the high divergence, but also this irregular pulse pattern. And you can see here, I've drawn a red circle, that it's not completely unimportant where the eye looks at. So here the most dangerous region, the hot spot, is on the right hand side. Okay, now as we have determined the basic parameters, it's time to choose the class, the laser class we want to evaluate. In our case, it's easy. We want to use our laser in public, so it's laser class 1. Next step is to determine the time base. The time base basically gives you the maximum time period you need to consider for the evaluation. It depends on the wavelength and also on the chosen laser class. Now we have determined the time base. The next step is the most complicated one, I'd say. That's the so-called angular subtends and the acceptance angle. So what is that? Let's assume a normal collimated or weakly divergent laser. This may be considered a point source, and a point source will be imaged onto the retina as a very small spot, so you will have a very high intensity. And that's why a point source can always be considered a worst case situation. However, I mentioned this before, VCSELs often do not come as single emitters, but as emitter arrays, and hence they can be considered an extended source. An extended source is a bit advantageous in terms of eye safety as compared to a point source, as it spreads the same amount of power onto a larger image on the retina, as you can see here in the schematic drawing. So depending on the extension of the source in XY direction, or it may also be a round source, and the distance between the observer and the laser source, the size of the image on the retina may vary. And of course, this is something that you may want to consider when your point source evaluation does not give you satisfying results. So you may come to the conclusion that assuming a point source does give you too high power and too restrictive AELs. You may want to consider the extended source situation. If you want to do that, you do not only have to consider the size of the apparent image, the so-called angular subtends. You also need to consider the accommodation of the human eye and the so-called acceptance angle. And the acceptance angle comes from the fact that you never know where the observer is looking and focusing at. So if you want to do the extended evaluation, considering an extended source, you need to do not only vary the distance between observer and source, but also the accommodation, this acceptance angle, within a certain range. This may become very complicated and you may want to use ray tracing to do that, but it may gain you a certain amount of power more as compared to a point source that you may send out of your laser system within the same laser class. Okay, now we have determined the angular subtends and also the acceptance angle, or we have assumed point source. And now we have all the parameters together that allow us to calculate the AE values, that is the accessible emission value, and that we need to compare to the so-called AELs. That's the accessible emission limits. Look at how this might work. So this is a table that I have copied out of the standard. And you can see that on the left-hand side, you need to choose the wavelength. We have determined, let's say, a wavelength of 940 nanometers. And then we have pulse length of nanoseconds. We have burst rates of milliseconds, and we have a maximum time base of 100 seconds. So the corresponding AEL is not a single value. It will be depending on whether you are pulsed or not pulsed and what other parameters you have determined. It will be a whole list of AELs, and you always have to choose the worst case. And then you will have your AEL. So what you need to check if all the accessible emission values are less than the corresponding AELs. If you find one single pair where the AE is higher than the AELs, you may restart from the scratch, choosing a higher class. This is not an option for us because we want to use our laser in public. So we need to rethink whether we can gain some margin here. If that doesn't work neither, we can still try to see if we can redesign the system a bit by, for example, reducing the repetition frequency or working with a shorter pulse width, and so on and so forth. There's always a few screws that you can tweak in order to improve your system. If you find no solution, you have to go to a higher laser class. If you have done this, you are still not completely done. You need to do some risk assessment as a very last point in the flowchart. You need to make sure that you have considered any possible failure that may arise and that may affect the security of your system. For example, a diffuser that increases the divergence and hence increases the intensity may break. So as a manufacturer, you need to make sure that you have considered any foreseeable fault condition and you have taken measures in order to protect the user. You are done and you have classified your laser. So that's basically it. My take-home messages for you today are VCSELs are lasers, and therefore they must comply with the IEC 60825-1 standard. They do have some special characteristics as compared to normal lasers. They are multimode, they are divergent, they are often extended, and they are often pulsed. These are all things that you need to consider if you want to evaluate a laser. Worst case assumptions, such as, for example, the point source assumption, will reduce the analysis effort tremendously. However, it may lead to restricted AELs. So you always need to compromise here. And my last point is, please, if you want to evaluate your laser in terms of eye safety, choose calibrated and traceable measurement equipment that satisfied the IEC 61040 standard. That's it. Thank you for your attention.